It's okay? Good. You hear me? It's okay? Okay. So what's program analysis? Well, actually, program analysis tries to find an answer to this observation by Dijkstra, that the only effective way to rise the confidence level in the program is significantly is to give a convincing proof of its correctness. So you need to extract information from code. So program analysis is designing an algorithm or a program here. This is a Turing machine that, given an input, that code provides all the invariants, all the assertions associated with that. So how to make it? Okay, so you have your program. And typically, you have an input, or a set of inputs, but in this case, one input, and then you look at the computation, and that's the semantics of the program for that input. And if you have another input, you may loop forever, and then the semantics is, I don't know, is nothing, is actually empty set. Okay, so this is the standard denotation of semantics, or trace-based semantics, if you want to have a fine grain. What's happening in program analysis? In program analysis, you are considering not single input, but sets of inputs or set of states. That means properties. A property is a set of states. Those states that satisfy that property. So if you have, for instance, that property I, that includes all those states, then the computation starts from all of these states. And it reaches that set, which is the property of the output. It's okay. So this is called collecting semantics. We collect all the states computed from the input invariant, for the input property. Of course, program analysis is useful for bug finding. And imagine that those are the bugging states, so the states that correspond to a bug. Therefore, you want to check if that specification spec is satisfied by the collecting semantics, so the property of the output. Is that true? Okay, so we see. So in this case, yes, you satisfy the property. It may well happen that if you enlarge the set of input for the same program, something bad may happen, so you reach that point. And that means that a bug happens. So the specification is not satisfied. Okay, what are the ingredients for program analysis? For building the algorithm. I'm Italian, so those are the ingredients I'm used to. Okay, so of course the semantics, trace executions, but this is undecidable. So if I want to find a property of program that is undecidable and I want to decide whether it's true or false, I cannot. So I need to approximate. There are many ways to approximate it. The first one, I stop computation after some while, but this is not program analysis. This is somehow partial execution, sorry, but you won't find those bugs that happens after. So engineers, here we are in the School of Engineering, they love making testing. You try some input and you run the code, but if you are lucky, you get the bug. Otherwise, it may well happen that the bug exists for some other inputs and you don't find that. So this is the idea of abstract interpretation, which is a theory behind program analysis. The only thing I know is probably abstract interpretation, so this is why I'm here trying to tell you what is program analysis from the perspective of an abstract interpretation guy, as me. And this is a younger example of an abstract interpreter. He's abstracting the interpretation by some two-level words, right? Yes, no, oh. Okay, so the semantics here is, well, if you run, for instance, this interval, along this interval, then you compute at each stage and you get so many intervals that are the intervals along the computation. This is not abstract interpretation. This is abstracting the concrete execution. Abstract interpretation is using this, what you compute at the first step, as the invariant for the next one. So you are computing in the abstract. You are not computing in the concrete, you abstract the output. You are computing within intervals in this case. So this is what's happened. You start with one interval, and then you get another one, but this represents all those states. Therefore, you start from all of them to produce the next step of computation, which is that interval here. And then you get the union of all of them, and this is the fixed point. In 3 steps, you get the fixed point. What's happened here? It happens that you get all the possible bugs and some false alarm because you are approximating. So you are losing the precision by generating an over-approximation, which is this. So the abstract interpretation, this one, is an over-approximation of the abstraction of the concrete interpretation. Good. How it works, the program analysis. Imagine that your space of states is a set of shapes. Okay? And I want to abstract that, so I approximate those shapes with one single form of shape, which is a circle. So I have many circles that approximate a star, a triangle, a square, a rectangle. In what sense? It's the closest circle around that shape. The concrete domain is a set of all possible shapes. The abstract domain is the set of all only circles that can be built around those concrete objects. It's way simpler, okay? This is the abstract domain. The key point that you will see in the papers of the session in program analysis is to build the so-called transfer function, how the concrete program executes on those approximated objects, which is not the real program, it's something different that has to be adapted to the shapes that you are considering the abstract domain. Okay, so program analysis should be sound, of course. What does it mean? Imagine that this is your specification, those are the buggy states, and that is this shape in blue is the real computed state. So the program computes that shape. So I want to approximate that, so I abstract that in the abstract domain, and I got the circle around that, because the abstract domain only considers circles. Then, of course, by computing, by the abstract transfer function, it may happen that the error accumulates during the computation. So I get a larger one. If that is included in the specification is proved. So the program is correct with respect to that specification. But it may happen that during the computation, the error accumulated grows, and grows in a way that it becomes incomplete. In this case, you get this. And those are the false alarms. Okay? Good. So program analysis is typically very different with respect to how you write code. For instance, these two programs are equivalent, but if you compute the invariant in the abstract domain of intervals, you get two different results. So equivalent programs may be seen different from the analysis point of view. It may well happen also that different programs can be seen equivalent from the analysis point of view. And this because the error computed by the analysis introduce spurious objects that makes the two programs equivalent. So what you will see? You will see a lot of things and beautiful things in the session of program analysis, so I suggest you to come and visit and see read the papers. The first one is a beautiful paper, really, on the use of polynomials. So imagine that the abstract domain now are polynomials. So the invariance you want to catch from your code is an invariant, which is a polynomial. The other one is a dynamic decreasability, which is made by computing decreasability over dynamically changing graphs. And this is very good if you want to analyze the dynamically changing code. So a code that has been patched, that has been adapted during the execution. This paper, which I'm one of the authors, is analyzing the analyzer. So if the analyzer if the abstract transfer function is monotone, then you are sure that with respect to some specifications, you don't have false alarms. And this proof is pretty interesting because we have a kind of proof system that allows to prove that the analyzer is monotone. Of course, it's undecidable, so sometimes you fail. The last paper is the distinguished paper, is FLAN. FLAN is a transformation, so a program specification, over a data log interpreter into a compiler. And this makes a combination of very sophisticated techniques, which are generative programming, modular staging, specialization, and flexibility. So thanks a lot for enjoying static analysis session. Any question? No question? Yeah, it's so abstract question that I have so many false alarms. Okay?